Hi, and welcome to 3.2 Free Fall Up. How could you fall upwards? In this lesson, students will be able to calculate and fully describe the motion of an object being thrown upward and find its maximum height. So, critical thinking. A ball is thrown straight upward. What is the velocity of the ball at its maximum height? What do you think? Pause the video. You could see this person, volleyball player, throwing the ball upward right around here. What would the velocity be? What do you think? What is the ball's acceleration at its maximum height? Interesting questions. Let's see if there's an answer on the next slide. So when a ball is thrown vertically upward, it has an initial velocity in the positive direction. In this example, let's say we throw the ball upward and that red velocity vector is showing positive 5 meters per second. The green acceleration vector is showing an acceleration of negative 9.8 meters per second squared. So the animation is going to move the ball upwards and the vectors will change, maybe. Will that acceleration vector change? Ask yourself, why is the ball accelerating? It's accelerating because of gravity. And just because you throw the ball upward in the air, is that going to really change the acceleration due to gravity because the ball is being thrown? No, Earth is exerting a gravitational force on this thing, causing it to accelerate. So it's going to stay the same. The acceleration stays the same. The thing that changes is the velocity. So the ball slows down at a rate of negative 9.8 meters per second squared as the ball reaches its maximum height. That velocity was positive, the acceleration was negative. They're pointing in opposite directions. So yes, it slows down to 0. So at the maximum height, the ball's velocity is 0 meters per second for just a fraction of a second, but the acceleration is always negative 9.8 meters per second squared. Just because that ball slows down to a stop, and then in the next lesson, it's going to come back down. But for now, we'll make the final velocity 0 so that we could calculate, okay, well, how far was it displaced in that positive direction? If we make the final velocity 0, then we could calculate what that displacement is and figure out what the maximum height is. Okay. So we can add some word problem vocabulary. We already know at rest means we could plug in 0 for the velocity. If it comes to a stop, the final velocity is 0 meters per second. And if it's dropped or dropped from rest, that means the initial velocity is 0 and the acceleration is negative 9.8 meters per second squared. And now if the problem says it's being thrown upward and it says at its maximum height or what is the maximum height, they're actually telling you not the height, but they're telling you you could use that velocity as described on that previous slide. At the maximum height, the velocity of the object is 0 before it comes back down, and then the velocity becomes negative. So Yosemite Sam fires his gun straight upward. A bullet leaves his gun with a velocity of 360 meters per second. How high does the bullet go, and how long does it take the bullet to reach its maximum height? So we'll start with an initial velocity is 360 meters per second upward. The final velocity is 0 meters per second because, like we said, that bullet is going, that's a bullet. It's going up in the air to a maximum height right here. Okay. So as it's moving upward, the velocity is decreasing because of gravity, negative 9.8 meters per second squared. And they're looking for the displacement. And we don't care about the final velocity. So look in your reference table. Which equation does not have, oh no, sorry, we don't have time. So which equation doesn't have time in it? We don't care about time right now. It's going to be the VF squared equals VI squared plus 2AD. And this VF squared is 0. VI is 360. 2 times, and it's very important, this is negative 9.8 because you're accelerating downward, you're slowing down. Your initial velocity is positive, your acceleration is negative. And then you can multiply by the displacement, which we'll calculate right now, 360 squared divided by negative 19.6. And you get 6,612 meters. Remember, we had to subtract the 360 over to this side, so that became negative actually. So it was negative 360 divided by negative 19.6. Okay, so that's pretty high in the air. The displacement is 6.612 kilometers, but we're talking about a bullet going up, and we're neglecting air resistance. So yeah, 6 kilometers sounds about right. All right, so then part B says how long does it take to reach the maximum height? And we actually rounded the displacement, so I'm not going to use that in my equation. So I want the equation without D. And we can use VF equals VI plus AT, or you could use the equation for acceleration. Either one will work. VF is 0 because it's at its maximum height. We're at 0 for a split second, and then this is 360 plus this is negative 9.8, and then we're solving for T. So T is equal to 36.7 seconds. So it takes 36.7 seconds to go up, and then if you neglect air resistance, it takes another 36.7 seconds to go down. Spoiler alert, those types of problems are in the next lesson. So it takes over a minute for the bullet to go up and then come back down, and hopefully by that time Yosemite Sam has moved out of the way. And that's about it. Thanks for watching. Have a great day.